This video has been supported by Welectron. Hey guys, a viewer has donated this delicious flea market find. It's a Fluke 731B solid-state DC voltage reference standard. None of this Western cell rubbish. In other words, the Fluke Model 731B is a versatile instrument providing stability while utilizing the excellent performance capabilities of solid-state technology. They specify a 1-year 30 ppm drift and a very short 30-minute warm-up time after power on. I'm surprised that this is still in a 1992 Fluke catalog. I would have expected it to be completely obsolete with the release of Model 732A, a direct successor superior in every way. We've discussed this one in another video and explored why in practice it's usually much more stable than its 1-year 3 ppm drift. Today's older, smaller, cuter DC standard does not have such a spotless reputation out there. But after having tested it for the last couple of months as received, I am pleasantly surprised. It's not bad. Maybe if we give it some love, we can make it very good. I believe this box may have been made in 1975. It can put out its central 10-volt reference and a few other voltages derived from that. It's much smaller than Fluke 732A because it doesn't have a built-in heater and no thermal insulation. But it should have a battery backup normally so that it can be unplugged and carried around without immediate ppm punishment. Of course, a very old age and internal batteries led to their usual conclusion. But it looks like somebody paid attention and evacuated the vicinity before too much damage had been done. All the beautiful precision circuitry lives under this simple sheet metal cover, all exposed to ambient temperature. There is no battery spill damage here though, and that's nice. I think only the lower half of the precision resistors, those classic translucent, wire-wound on mica card Fluke resistors, and the two axial hermetic ones in the middle have an impact on the central 10-volt reference. The entire upper row of custom value hermetic resistors is only there to divide down the central 10 to all the other output voltage options. Man, what an overkill. I'll atomize this thing as much as possible for easiest battery spill decontamination. And of course replacement of all the organic perishable components, the carbon resistors and electrolytic caps which are miraculously still somewhat intact. There are a lot of in- and output pins on the reference assembly, but don't be fooled, this whole device is pretty simple. Love the star ground and the star 10-volt layout on the back of the board. Strangely, U2, the central ref amp that this impressive entourage of precision resistors serves, is decorated by a rare Siemens und Halske logo. I always thought these standards were all based on Motorola SCA263s. Apparently not. This part must be functionally equivalent, but it says DH80417B on the side. And it might be a 17th week of 1975 date code. Some EEV Block forum members have spotted this part with the nowadays totally unknown Dixon Electronics logo. I'm not sure if some flux and hair monster has been in here before me, or if this satisfied some post-manufacturer inspections in the 70s. It doesn't satisfy me, that's for sure. It's pretty grimy. And a lot of the traces and through-holes seem to be reinforced with copper wire and solder. As if they didn't quite trust their PCB manufacturer. They probably didn't know about PCB way back then. Let's take a peek into the instruction manual, more specifically the theory of operation section. Turns out this is the same circuit that we found at the center of Fluke 732A. It's based on an internal reference voltage, not yet 10 volt. More like a 6.2 Zener voltage with a slightly positive tempco, plus a transistor's 0.5 base emitter voltage with a slightly negative tempco. These two semiconductor features with opposing temperature coefficients are on the same substrate and in the same metal can component. U2, the one with the mysterious Siemens und Halske logo. Through proximity and thermal coupling, these two unwanted temperature coefficients can counteract each other. And through careful design and fine-tuning of the surrounding circuitry, they can be convinced to very nearly eliminate each other. The schematic view from that same manual has a few hints about how this complex fine-tuning may have happened. Imagine TP1 and therefore the Zener anode being 0 volt, and TP2 later becoming 10 volt, then R4 determines the Zener current, and therefore the reverse voltage and the temperature coefficient of the same. There is no little triangle footnote attached to R4, so I assume that part is fixed in all implementations. Oh, all of this shrubbery is just dividers for the other outputs, completely irrelevant for us now. U2 and these two resistors have a footnote though. They are part of a ref amp set, a magically factory pre-selected team of components that shouldn't be tinkered with, according to that factory. These matched ref amp sets are used in other Fluke products too, I assume, like early calibrators and voltmeters. The resistors are placed in the path of the collector current that U2 is going to allow through. As a consequence, there is going to be a voltage drop over these resistors from the 10-volt node to U2's collector and an op-amp's non-inverting input. That collector current is U2's base current times the transistor gain beta, and dear God, where am I going with this? Does anybody remember Kirchhoff's circuit laws? Anyway, the ref amp set, node 1, is custom tailored to give every specimen of U2 a suitable collector current at which it exhibits a low output voltage temperature coefficient. Because of the early effect, a variation of the effective width of a... No, stop it, Raps. That is enough information about this small detail. Go to the next one. Okay. The selected resistor set for node 2 forms a voltage divider that, if TP2 is 10 volt, produces something very close to the Zener voltage plus the transistor's VBE. If TP2 was at a higher than intended voltage, the divider output would also be higher than V Zener plus VBE, and a small current would begin to flow into the transistor base. That current would be amplified, it's what transistors do. And the increased U2 collector current would lower the op-amp's non-inverting input voltage, ultimately causing the series pass transistor Q1 to be driven less hard, and the whole reference circuit being starved exactly until a precise 10 volt appear at the TP2. Wow, it's not that complicated, but it takes a lot of grunting to convey. I'll link the usual Felstat sketch with my component values below, just in case there is somebody out there who still hasn't had enough of this circuit. It is, as far as I can tell, still the same circuits that Fluke's modern-day $10,000 voltage standards are based on. Those just get a few more tricks, such as compensation for voltage drops over PCB traces, and more modern U2 ref amps, called LT Flu nowadays. Keep an eye on TP, the 10-volt output, while I change the factory-selected Node 1 ref amp set resistance. See, a huge resistance change has very little impact on the 10-volt output. That's why they got away with small, normal axial metal film resistors in that position. Good enough for roughly setting the tempo. Similar story for this collector current set point divider, and the Zener current setting 1.27K. Drift of those parts has an attenuated impact on the 10-volt output. Although here they had higher quality resistors custom wire wound for the actual circuit. This divider, however, for the crucial Zener plus VBE comparison, is massively impactful. Drift anywhere in this chain directly translates to error in the reference output. So for this function they probably used the best resistors available at the time. A pair of hermetically sealed wire wounds, maybe even selected for a matching tempo. And this is where I could kind of imagine a small improvement. Don't get me wrong, I've compared this Fluke 731B with the average of the best of my ADR muse for over 3 months, and saw only 0.7 ppm deviations as opposed to the 15 ppm spec for that time period. It's doing great, but I feel like it could be better. Should we give that a try? Do I even have to ask? First I'll do a temperature sweep of the normal unmodified board as delivered by Fluke. I'll power on only the reference board inside of my copper thermal test chamber. I'll set the Arroyo tech source to 19 degrees Celsius and let it all soak for a few hours, before starting a slow sweep from 19 to 35 degrees Celsius and back. I'll use Keysight 3458A to record the 10-volt output the entire time. I've published my Python scripts for this kind of stuff as multi-instrumentalist on GitHub. I let this operation run overnight, but it was probably still too fast. And I caught some strange, inexplicable downward spikes. Still, ignoring those, a fantastic 725 nanovolt per degree Celsius, or 0.072 ppm per Celsius temperature coefficient is visible. A modern, ovenized Fluke standard is specified to 0.04 ppm in this category. So this is already impressive, but we can do better, I'm sure. Most importantly, that trim potentiometer needs to go. Sure, it lets me dial in 10.0000 volt exactly, but I feel like I can never really trust potentiometers. I'll trade a large number of zeros for long-term stability any day. I also thought for sure that I could just replace this LM308H operational amplifier, 1975 edition, with basically anything modern, to get me a substantial, effortless improvement through half a century of op-amp development. But I'm not sure about that anymore. LM308 has a special comp pin, with which one can influence the part's frequency compensation. In this strict DC-only application, the Fluke engineers decided to overcompensate that part with a 100 picofarad silver mica capacitor, degrading its AC performance, to the benefit, I guess, of its DC specifications. Oh well, I'll swap a few bits and pieces around, and see if I can eke out at least a few little improvements. Let's take care of a few other chores while I'm testing some precision resistor alternatives, in some more of the ever-popular 6-hour temperature sweeps. Normally, I wouldn't disturb the ancient precision resistors that have been settling down in their respective positions, for much longer than I've been alive actually. Oh, why is this one sticking out so far? But I've got many good voltage standards now, so I'm not feeling too much remorse about tinkering with this one. What passes for a mainboard around here is also very simple. It's basically just power transformer configuration, rectification, and a 1 resistor trickle charger for what used to be a nickel-cadmium battery pack. The resistor for that trickle charger is a carbon composition type, which I cannot tolerate obviously. It used to be a 510 ohmer, which conservatively should never deliver more than 40 milliampere. At first I wanted to go with a close to original nickel-cadmium pack again, but only these thick cells were readily available. It would have been a major struggle to fit 15 of those into the slender Fluke body. A more attractive option I had on hand was this sealed lead-acid battery. These are also trickle chargeable, which is neat, but Fluke's reference circuitry needs a few volt of headroom above the 10 volt output. The nominal 12 volt of this one wouldn't be enough, I'm afraid. So, never thought I'd have to do that one day, but I ordered these 2 nickel metal hydride packs. Not a terribly sexy battery chemistry, this one. I wish I could fit an SOK server rack module in here. But this will do. It's trickle chargeable and it fits this existing bracket beautifully, with a bit of foam cushioning and longer screws. If only we had a super sensitive, isolated AC-DC current and voltage measurement tool to see if the trickle charging circuit isn't up to anything nefarious, and to quantify the common mode leakage current, in other words the quality of the guarded transformer in here. Oh, what is this? A Joulescope JS220, what a coincidence. This is a precision data acquisition system primarily intended to analyze power consumption of medium to super low power electronics. In its most sensitive current range, it can literally see nanowatts with plenty of resolution. That's not really my niche of interest though. I enjoy the floating AC-DC current measurements of the isolated front end. Those can be displayed in real time in an oscilloscope view, to catch rare wake-ups of normally sleeping hardware, for example. Or the fact that the trickle charger in here, while not trickling any harder than 6 milliampere, does seem to have a strange half sine wave shape. I'm not sure if that's allowed or a good practice for charging nickel metal hydride. I can't think of any reason why not, but it doesn't feel right. Leave a comment if you know anything about this. Ironically, the Joulescope voltage input, having a gigantic input impedance, can be turned into an even more sensitive current input by placing a high resistance shunt such as 10 meg across it and just reading voltage drops over it. This way we can measure Fluke 731B's common mode leakage into Earth precisely. It's sinusoidal in shape, of course, because there are no crazy DC to DC switchers involved, and it comes out to 0.2 microampere RMS and 0.6 microampere peak to peak, surprisingly better than the successor Fluke 732A, but not quite as good as Keysight 3458A or Fluke 5700. Shoutout to Joulescope JS220, available through the manufacturer worldwide, or in stock in the European Union at our sponsor Wheelectron.com. The front panel is pretty rough, by design, and it's all scratched up too. There's an on-off switch on here that really rustles my jimmies. If there is one thing you don't want on a voltage standard, oh well, at least it's one of these locking collars that you have to pull on to move it. I'd love to amputate that switch entirely, but it doubles as a holder for the panel meter that should show battery state of charge later. Yep, they are not messing around. One of these disconnects mains from the power transformer and the other one disconnects the battery. One thing I do like about this is that both of these power lines are shielded, or guarded if you will, to minimize mains to secondary capacitance and therefore common mode leakage current. The ways of batteries builds are inscrutable, and so on this whole assembly, only the outer nut that holds the power switch happens to be corroded and sprouting colorful crystals. I'm replacing that, but for the record, I'm still not on good terms with that power switch. Nickel-cadmium cells commonly use potassium hydroxide as an electrolyte, a strong base whose remains we can try to neutralize with mild acids, such as vinegar or citric acid. Not sure if that makes sense though. The chemical reaction here has probably halted decades ago, and we are tarnishing the tinned traces superficially with an acidic cleanup, so maybe some mechanical scraping would have been sufficient here. The front assembly also has a large multi-turn potentiometer, but that is not involved in the 10-volt formation, so it's allowed to stay. However, it's missing a little multi-turn readout. These have apparently been mechanically interchangeable since forever, so I finally get to use this ancient piece. With that, one can apparently use Fluke 731B as an adjustable microvolt source. I've got something better for that job, but for completeness sake I'll fit this on here. Pretty good so far. And of course I couldn't not mention the nice gold-plated tellurium copper binding posts. And here it comes, the long-awaited reference assembly. It was pretty good before, as I said, and so it's absolutely unreasonable to give this such a fundamental makeover. A 10-volt potentiometer substitution would have probably been all that this thing needed. But I just wanted to see how far I could take this ancient SCA-263 predecessor, with mostly modern-day bulk metal foil resistor technology that I already had on hand anyway. I replaced the collector current setting voltage divider with a 2K 5K VHD200. Grudgingly, I put the 1.27K Fluke mica card wire wound back in its position, just on longer legs which I used to test drive a few other precision resistors from my arsenal. The Note 1 factory selected ref amp set, remember? Is the one I spent the most time on fine-tuning. All the other modifications have thrown the previously fine-tuned Tempco out of whack. Now it's dominated by that blue 25K bulk metal foil SMD resistor, and fine-tuned to perfection with a few axially leaded parts. The only replacement about whose wisdom I'm pretty sure is the 10-volt feedback. Previously, 2 hermetic wire wounds, a trim potentiometer, and 2 brown mica card wire wounds. Now it's all in a single 10K 5K VHD200, an $80 part from whose superiority we are directly benefiting. I hope. If not, I can always fall back to the original stuff, of course. Having lost nothing but a bit of time, and yeah, looking at the under construction state of the PCB, you can guess that I am indeed expecting to do that at some point. Unless this turns out to be a stability world record breaker now. I wish I had a Stargate-themed Soviet hand multimeter to test that. Oh. Well, I guess I've got to do a few more Arroyo and 3458A runs then. Oh, what is this? Is that a Stargate-themed Soviet hand multimeter? What a coincidence. Yeah, looks good. The output is now stuck on 10.08 volt. Not as pretty as a ton of zeros, admittedly, but for my purposes functionally equivalent, and certainly much more long-term stable. We are absolutely certain about that, aren't we? I'll link the original and modified component values below. I didn't quite reach the 0.04 ppm per Kelvin temperature coefficient. That is quite doable with ovenized parts, but I did manage to improve the original 0.72 ppm per Kelvin ever so slightly. All of these numbers tested between 19 and 35 Celsius. I'm not seeing a big change in the low-frequency noise department. Unsurprisingly, because I didn't change the Zener current, which should be the largest contributor of that. What little change there is, I would accredit to the standard now being battery-powered, as opposed to mains only before. Most importantly, I'll add this new old standard to my automated data logging setup, where a scanner card is used to establish one-to-one connections between all combinations of voltmeters and standards, so that voltmeter drift can practically be eliminated by only looking at differences between standards. I'm pushing all of that data to the ADRMU GitHub repo if you want to have a look. But that's pretty much all for today. We will know more about the success of this operation in a few months or years. Sorry for the cliffhanger, but that's the timescale of these things. Thanks to the viewer for donating this cutie, and thanks to Wheelectron for sponsoring this video. Check out their Joulescopes and JBC soldering tools to boost your electronics business or hobby.